Welcome back, coders. In this video, we are looking at an approach to Advent of Code 2022, Day 12. In this guide, we will be implementing an algorithm called breadth first search. Don't let that intimidate you. I will be breaking it down into testable chunks that I believe anyone who has learned the basics of coding can accomplish. More specifically, this puzzle uses two-dimensional arrays, loops, lists, and a few custom data types. That's it. Although this guide is only covering an implementation for part 1 of this puzzle, the solution you will get will be very helpful for part 2. And at the end of this guide, I will be giving you a few tips on how you can adjust your solution to solve part 2. I've posted a link to the puzzle in the description below this video. Of course, if you get stuck, don't hesitate to post your questions in the comments or make a post on the Advent of Code subreddit. There are tons of people there that would love to help you out. And if this guide is helpful, let me know by clicking that like button. And if you want to see more Advent of Code guides, be sure to subscribe. With that, let's get into it. Having collected your items from the troop of troublesome simians, you attempt to contact the elves using your handheld device. Unfortunately, the river you are following is too low and you cannot get a decent signal. Browsing through your file system, you discover that your device has a height-o-matic program. Running the program reveals a height map of your local area. Lucky you! There's a large hill nearby. Can you calculate the shortest path to the top of the hill? Captain Coder here with day 12 of Advent of Code 2022, and I am pumped up because I love hiking and I'm ready to get up this hill. That said, it is always important to break down each problem so we understand what our inputs are and what our outputs should be. In this puzzle, we are going to receive a two-dimensional grid representing a height map of the surrounding area. So if we scroll down here, we have an example. We're going to get this two-dimensional grid with a bunch of letters on it. The letters represent our heights, and they are sorted in alphabetical order such that A is one lower than B, B is one lower than C, all the way up, so you have Y is one lower than Z. So it's sort of in alphabetical order, A to Z. There's also two special characters on our map. We have an S, and the S is where we're going to start on the map. This can actually be anywhere. It's in the top left corner, but it can be anywhere on the map. The height of the S is the same as A. And then we have another special character, E, which is the end of the maze, and it has a height that is the same as Z. And then we are being asked to calculate the minimum number of steps required to go from our start to our end. But we cannot go directly from our start to our end. The heights determine which spaces we can move into. The rules work this way. If you're on the same height, you can move into that space. If the height's less than where you are, you can move into that space. And if the height is one greater than where you are, you can move into that space. So you can go up one step, jump down any number of steps, or move on a flat plane. Any other configuration is not possible. You can't move off the edge of the map, and you cannot jump. So if you have a height difference that's more than 1, you cannot move there. For example, if we look at this position here, C, we can move to the adjacent spaces that are C's, but we cannot move to the adjacent space that is S because S is too far above the C. This A here, we can move into the spot north of it and south of it, but we can't move to the east because C is too far above. In this spot, A, we can move north because S is the same height as A. We can move south because there's an A, and we can move to the east because B is only 1 greater than A. If we are in a Z position, we can actually move to any space that's adjacent because Z is the highest position. So we have a very straightforward problem description, but the solution is not entirely obvious at a glance. So let's talk about a strategy. It turns out there are a bunch of ways to do this, but in this guide, we are going to be using an algorithm called breadth first search. This is an algorithm that is often used to solve mazes, And with that in mind, the super high level strategy is to translate our height map into a maze such that the passageways between locations are determined by their relative heights. To do this, we are going to define a few types. First, a position type, which will represent the rows and columns within our maze. Second, a maze type, which will be capable of determining which positions are neighbors to each other. And then third, we are going to implement an explorer type, and the explorer is going to have a method which explores the maze incrementally, tracking the distances between each of the positions it visits. After we've defined and tested these types, we need to parse our puzzle into that model. And with that model parsed, we can iterate, calling the explorer's explore method until it has reached the end of the maze, at which point we can report the distance from the start to the end of the maze. Whew, that's a lot. Are you ready? Let's go. The first thing we are going to do is define a position type. We need to be able to track rows and columns within our height map. I use rows and columns. You could use XY, but when we're dealing with the two-dimensional arrays, I find it easier to think about it as row and column. So I'm going to be using row and column for that reason. I've written a test here for my types. I've defined a basic type where I can create a position with a row and column as input. And then there's going to be a method I'm going to write, neighbors. So our position is going to be able to tell us which neighbors it has. And this is actually going to be regardless of a height map. A position can just tell us what its neighbors are to the north, east, south, and west. In this case, we are going to make it return in that order, north, east, south, and west, so that we can test, when we get to testing how our explorer moves around, it's going to be important to know which order those come in. So see if you can write yourself a test. My test here, I have my position, p.neighbors. I get a list of positions back, and I'm expecting it when I'm at 0, 0 to get a north, east, south, and west. And I'm using rows and columns, so north is 1 less than the current position, and south is 1 greater. So rows go up north and down south. I also want to make sure, give myself confidence it's going to work for different positions. So I've gone ahead and done it for position 3, 2 as well, and I've defined my north, east, south, and west. Go ahead, write yourself a test, do an implementation, and see if you can get it to pass. Here I am, my test neighbors is passing, and I'm about to show my solution. If you don't have a passing test just yet, feel free to pause, but here it is. I've defined my position as a record type in C#. In your language, you might be using a class or a struct, or whatever your language happens to provide. I have an int row and an int column. For convenience, I have defined 4 properties here, north, south, east, and west, which will get me the appropriate neighbor. And then my neighbors method here returns a list, and I just pass it in north, east, south, and west. Next, we are going to define a maze type. This type is a wrapper for your height map. In this case, I've defined it as taking in an integer array, 2-dimensional array of heights, and I'm going to implement one method here. The important method here is find neighbors. Given a position, give me back a list of neighbors that I can go to from that position. But I'm going to define 3 methods total. There's 2 helpers down here that I think might help you implement this rather than doing it all in one big go. I'm going to write contains. This is going to take in a position and tell me whether or not that position actually exists on this map. This will be useful for checking whether or not a position's neighbor goes outside of bounds. Then I'm also going to implement a check move, which takes in 2 positions, a from position and a to position. It's going to return false if either of those positions are not on the map. And then it will also check to see if the from position can move to that to position, returning true if it can. finally, with those two in place, it becomes relatively easy to iterate through a position's neighbors and determine whether or not they should be visitable. And you know me, I've written some tests here. The first test, find neighbors in all directions. So this is a case where I'm starting in this center position. I've created a test height map. Starting in this center position, I should get back north, east, south, and west. So when I call my find neighbors on the center, I'm expecting to get the neighbors north, east, south, and west. Right now it's failing because my implementation just returns an empty list. This test here currently is passing find neighbors no directions. So if I'm in this center position, every space next to me is too high. So I get back none. This is passing because, again, my implementation currently returns nothing. Find neighbors different heights. So this one gives me a little bit more confidence that it's working for varying heights. I'm not going to get a north here because it's too high. I'm going to get a 2 because it's only 1 higher than the center. I'm going to get south because the 0 is below the 1, but I'm not going to get the 3 to the west because it is higher. It's too high for the 1 to get to it. Finally, I have one called Find Neighbor Corners, which is just a little sanity check that when I check each one of my corners, I'm only getting back the appropriate. So in the top left, I should only get the east and south. In the top right, I should only get the west and south. In the bottom right, I should get the north and west. And in the bottom left, I should get the north and east. So I've written out those tests here to give me confidence that when I'm done with my implementation, it is going to work on a bigger maze height map. So see if you can write a test for yourself, write your implementation, and then see if you can get your test passing. Good luck. If all went well, you now have a passing maze test. If you don't yet, go ahead and pause because I'm about to show my solution. Here it is. My find neighbors works the following way. I take in a position, I iterate over the neighbors of that position, so all of the neighbors, north, east, south, or west, and then I check the move from that position to the neighbor. So if my check move returns true, I save that neighbor, and then I return it. Because I have a list with a known order, that order is also preserved by this method. Let's look at our 2 helper methods here. First, we have a contains. This is just a bounds check, a sanity check to determine if this position that is passed in actually exists somewhere on this maze. And then check move checks if either of the positions from or to does not exist on this maze. We return false because we cannot access it. Otherwise, we extract the heights, the to height and the from height, and we check, is the height we're going to less than or equal to our from height plus 1? So this is important here. Our to height needs to be less than or equal to our from height plus 1 because we can only go up 1 step, but we can go down any number of steps. Next, we need to implement an explorer type. But before we do that, let's take a look at the breadth first search algorithm. Right here, I have defined 2 arrays. One array is the heights of an example map that we might explore. And the other is going to be the distances to each one of those positions. I've specified that I'm going to start my search at position 1,1, which is right here. And because I'm starting there, I'm going to mark that it takes 0 steps to get to the start position. Next, we are going to add that start position to our exploration queue. The exploration queue defines the order we are going to visit each of the positions on our map. When we visit a position, we examine each of the neighbors that we can access from that position and update that position's distance
based on the position we're exploring from. For example, in position 1, 1, we have one neighbor we can visit to the north. The neighbor to the east and to the south and to the west are too high to visit. So I'm going to update the distance to the neighbor to the north, setting it equal to 1, 1's position plus 1, which happens to be 1. Then I'm going to add it to the queue. Having completed exploring position 1, 1, I remove it from the queue. This marks a single exploration step. Let's continue. I examine the front of my queue. I'm looking at position 0, 1, which happens to be this one here. I look to the north, there's nothing there. I look to the east, I can visit this position because it is at a height of 2 and I'm at a height of 1. So I add it to my exploration queue. Then I update my distances by setting the position 0, 2 equal to the distance of the node I'm coming from plus 1, which happens to be 2. I look to the south. I can visit that position, but I see that I've already explored it and can get there in 0 steps, so I move on. I look at the position to my west, and I can explore it, so I add it to my queue. And I update the distance to be equal to the distance of the node I'm exploring plus 1, which happens to be 2. Having finished exploring position 0, 1, I remove it from my queue. This marks the end of another exploration step. Let's go ahead and do one more. In this case, I'm examining position 0, 2. So row 0, column 2, it's this position here. I look to my east, and I cannot go that direction, so I skip it. I look to my south, and I can enter that position, so I add it to my queue. I update my distances to be equal to my current position plus 1, which happens to be 3. I look to the west. I've already visited this. It has a shorter distance of 1, so I move on. Having completed exploring this position, I remove it from my queue. If we continue performing exploration steps, we eventually will fill up this grid with distances from the start position to each other position. To save you a little bit of pain, I've gone ahead and sped up this video here so you can see the breadth-first search being solved by hand. As you go, you're just going to keep pulling things off the front of your queue, exploring that location, updating your distances, and then checking the next location. If I continue this process, eventually my exploration queue will be empty and I will have filled in every space that is reachable from my start position. In this case, I was never able to reach the position 2, 0 because it is not reachable from any of its adjacent spaces, but I know the distance from the start position to any other position within my height map. All right, at this point, I hope you have a basic understanding of breadth-first search, and you're going to be implementing that here in an Explorer data type. So I've gone ahead, defined a basic Explorer data type here. It has a map property. This is going to be our maze. It has a position start. This is where we're starting when we do our exploration. I have this exploration queue. I'm using a queue type provided by C#, but a list or an array works just fine as long as you're pulling things off the front and adding things to the end. And then here is my two-dimensional int array for my distances that I'm going to keep track of. When I construct this explorer, I'm going to take in a maze. I'm going to take in a starting position. I'm going to set those two things. I'm going to then initialize my distances such that they are all -1. -1 is going to represent a position that has yet to be explored. At the end of exploration, this will mean that the position could not be explored. Next, I'm going to go ahead and set the distances for my start to 0 because it takes 0 steps to get to the start position. I'm going to create a queue here, my exploration queue, and I'm going to go ahead and add my start position to it. All right, the moment we've all been waiting for, the actual
implementing of the breadth first search of the explore method. I've written a helper here called isExploring. This is going to tell us whether or not we have finished exploring. It's going to return true if there is more to explore. And then we have this explore method. It's going to return the position that we just explored. So if we have nothing left to explore, we're going to throw an exception saying that there's nothing left to explore. Otherwise, we're going to dequeue our position that we're going to explore and eventually return it. In this spot here, we have to do a couple things. We are going to get all of the neighbors of this position. We're going to iterate through them, checking to see, have we been there before? Do we have a distance for them yet? If we do, we skip them. If we don't, we are going to update our distances array to be one more than the distance to the position we are currently exploring, as well as in queuing each of those neighbors into the exploration queue. And you know me, I've written a test. This test is actually the example that I just showed earlier in the video. We have these heights. I initialize my maze. I create an explorer starting at position 1, 1. After it's constructed, I check to make sure my queue contains that start position and that I am exploring. My queue should have just that one start position. Then I call explore. After calling explore, I know that the position to my north should have a distance of 1 and that my queue should now contain that position. If I continue calling explore, it's going to get the positions of the east and west from that location and add them to the queue. This process continues until I've explored everything and my isExploring returns false. So go ahead, write yourself a test, see if you can implement the explore method, and of course, good luck. I hope you're smiling. I hope you're happy. I hope you have passed your tests. If not, go ahead and pause, keep working on it, and I'm going to show you my solution. Here I am in my Explorer. I have my explore method. I'm dequeuing the position I'm about to explore. I'm finding all of the neighbors that I can visit from this location. I check, is the distance of this location currently -1? If it is, I know that I can get there in the number of steps it took to get to the position I'm exploring +1. So I update my distances and then I enqueue that neighbor. Finally, after I've done iterating through all of my neighbors, I return the node that I just explored. We're so close. All that we need to do now is parse in our inputs into a data structure that we can use. In this case, I've defined a data type just called puzzle to be a wrapper for all of the components of the puzzle. It has a maze, which is going to represent the terrain. We have a start position and an end position. And I've written a stub here for my parse, which takes in an array of strings, which are the rows of my input, the character that I'm going to start at, and the character I'm going to end at. I then initialize an int array, a two-dimensional int array, a start and end position. I'm going to loop through this, pull out the appropriate pieces, and then return that new puzzle. I've also defined a little helper here that I recommend you use as well, which is going to take in a character and return to you a numeric value. This is a way you can convert it very easily. With ASCII, we can just do letters like this, character minus lowercase a. That'll give you 0 for A, 1 for B, 2 for C, etc. For E, I've done Z minus A because E is the same as Z. And for S, I've done 0, which will be the same value as A. Of course, I've written a test here. This test is on the input that we receive as the example. And I've gone through and figured out by hand what all of the heights are. This might be a little bit overkill. but I'm going to check that this expected value is in fact what I get when I parse my puzzle. Go ahead, write yourself a test, see if you can implement your parse method, and good luck. Hopefully everything's gone well and your parse method is working the way you want it to. If it's not, go ahead and pause. I'm about to show my solution. Relatively straightforward here. I loop over my rows and then loop over the columns, keeping track of my index as R and C. I pull out the character from that row and column. I check if it's my start character. If it is, I set my start position. If it's my end character, I set my end position. And then I go ahead and set the integer value in my height map at that row and column to be the character's height. After I'm done iterating through all of the characters, I simply construct my puzzle, create a maze with those heights, give the start and end, and return that. With our input parsed into a maze and a working explorer, we are ready to solve this puzzle. We are going to do this by reading in our input into an array of strings. We're going to construct a puzzle by parsing it in, specifying S as our start and E as our end. We're going to construct an explorer. We're going to give it that maze and the starting position. Then we're going to loop, checking, has our explorer finished? If it hasn't, we're going to explore its current position. If that position that we just explored is the end of our puzzle, we can stop. We look up that distance from the start and report it. Go ahead, give it a shot. I'm very happy. I hope you're happy too. My program is reporting that the shortest path has 31 steps, which is what our example should produce. If you're not there yet, go ahead and pause, see if you can get it working, then come back and check out my solution. Here it is. I read in all of my lines into a string array. I build the puzzle using my parse method. I specify that I'm starting at S and ending at E. I build an explorer, giving it that terrain as well as the start position. While my explorer is reporting that it is still exploring, I explore the current location. It gives it back to me. I check, is that current location the end of the puzzle? If it is, that means I've reached the end and I can stop. And I display the shortest path has, and I look up the distance from the start position to that current location. With that said, all that's left to do is download my input, pass it in, cross my fingers, and if I'm lucky, get that beautiful gold star. I hope you found this guide helpful. I hope you were able to get your beautiful gold star. The second part of this puzzle, let's look at it real quick and talk about how we might modify our solution for part one to solve it. The second part of the puzzle is asking us to find the shortest path from any A position to the top of the mountain. One way you might do this is to find all of the A positions, then compute the shortest path from each one of those to E, then loop through all of those, pick the one that's shortest and return it. That is the simplest way you could do it, though it's quite inefficient. If we think about the puzzle a little bit differently, what if we start at the top, work our way down until we find the first A we encounter? So we're gonna do a breadth first search from the top down. As soon as we find any A's, we stop. So in this case, we might modify our program a little bit so that instead of S being our start position, E is our start position and A is our end position. This won't quite get you an answer right away because when we're going downhill, we can jump off ledges. To solve this, you're going to need to modify your maze class. To do this, you're going to want to modify the check move method in your maze so that way it checks that the to position is capable of moving to the from position. I hope these hints are enough to get you there. As always, best of luck. Hopefully at this point you've submitted your solution and received a beautiful gold star. I hope you found this video helpful. If you did, let me know. Click that like button. If you want to see more Advent of Code guides, click subscribe so you'll be notified when they're uploaded. And as always, have a beautiful day. Keep on coding, keep on growing, and you're welcome back anytime.